and welcome. I'm Caro from CaroMaths, and in this video I'm going to give you an introduction to integral calculus, also called integration. It's actually been suggested by 2 of my Instagram followers. And normally I wouldn't start talking about integration until I've covered differentiation, because integration is effectively the reverse of differentiation. But because it's been requested, I thought I'll do it anyway. But just so you know, before you watch this video, you should have at least a basic understanding of what differentiation is and of how it works. It'll just help you follow me a bit better. And to start off with, what is integration? Well, integration, we're trying to effectively find the area under a curve, and I'm going to show you how to do this. I'm going to talk to you about the notation, and I'm going to give you a couple of examples at the end. So let's start. So as I've just mentioned, with integration we can find the area under a curve. But how exactly do we do this? Well, let's have a look at this graph. But before I go into how we do this, I just want to give you an overview of what you can see. So on the left, the vertical axis is called the y-axis, and the horizontal axis is the x-axis, and the green line, the green curve, is our function of x, f of x, which is equal to y. So if you don't know how to do integration, then you think, well, it's quite tricky to be able to calculate the area under the curve. So what could we do? Well, we know how to calculate the area of a rectangle, right? Because you just have the short side times by the longer side, and that gives you the area. So what we could do is we could estimate the area under the curve by slicing the curve into many different rectangles, like I've done here. You can see I've sliced it into 5 rectangles in this case, and the shaded blue area is approximating the area under the curve, but you can see that on the left and towards the middle it's overestimating, and then on the right it's underestimating. So you could think, okay, so roughly it's going to even out and it's going to give us roughly the area under the curve, but it's not going to be very accurate. And just to explain the terminology at the bottom, so you've got our slices are 2 squares wide, and underneath, so that's the delta of x, so that's the width of the rectangles. Have you got an idea of what we could do to make the area under the curve that we're estimating more accurate? Yes, that's right. We could make the rectangular slices narrower. So let's have a look. Here is exactly the same graph as you've seen just now, but the rectangular slices, they're now just 1 square wide instead of 2 squares wide. And you can see that on the left we still got some overestimation, and on the right we still got some underestimation. But hopefully you can see that it's much more close to the actual area under the curve that we're estimating. So as the slices are getting smaller, the error is getting smaller. Now we could take that to the next level, where we just have very, very fine slices, as you can see here. And now we're actually estimating the area under the curve. So the error of the estimation tends to 0 as delta x tends to 0. But now you might say, well, that's great, Caro, but I can't sit there all day adding up area of very, very thin slices. And I agree, you can't. So that's why I'm now going to show you how to do the integration. Now let's have a look at the notation of how to actually write this before going on to solving a couple of examples. So this is the notation, and don't be worried looking at it. I'm going to tell you exactly what each thing is. And firstly, how you say it is you say it's the integral of our function of x dx. And note that I'm talking about just indefinite integrals at the moment. There's also something called definite integrals, where you calculate the area under the curve between 2 points. But for now, we're just looking at indefinite integrals, where you look at the whole area under the whole curve. So the green squiggle, it looks a bit like an S, because remember we're really summing up lots and lots of little slices. Well, that's just the symbol for integration. And f of x is our function that we're integrating. And dx, it just means that the slice is approaching zero width. So with our graphs, first the slices were 2 squares wide, then they narrowed to 1 square, and then they were only really a very thin slice approaching zero width. Great, so now we know how to write it, but how do we actually solve this? Well, once you know the rules, it's not actually that tricky. So basically you've got the integration of x to the power n dx, then that's equal to x to the power n plus 1 all divided by n plus 1, and then you need to add a constant. And you need it because when you differentiate x squared, for example, then you get 2x, right? But if you differentiate x squared plus any number, whether it's 8 or 64 or whatever number you choose, the answer is always 2x. So when we reverse this, we only have 2x, and the constant could be any value when we integrate it. So we just wrap it up by calling it c. And my maths tutor, when I was studying A-levels, he gave us a very good way to remember how to do integration, and I actually remember it to this day many years later. So I want to share it with you, and hopefully it'll just stick in the back of your mind. So what he told us is to do integration, you add 1 to the power and divide by the power so formed, and then you add your constant. And you can see that, right? It should be quite obvious. So we're integrating x to the power of n. So we add 1 to the power, so it's x to the power of n plus 1. And then we divide by the power we've just formed, which is n plus 1. So hopefully that makes sense. If not, drop a comment below and I'll explain it in a bit more detail. And now let's put that theory into practice by looking at a couple of examples. The first example I've got is the integral of x squared dx. And I'm just going to give you a moment so you can have a go yourself. Did you manage to do it? Let's have a look together. So what is it? Add 1 to the power and divide by the power so formed plus the constant. So we're adding 1 to the power, which gives us x cubed, and divide by the power so formed, which is 3. So it's x cubed over 3 plus our constant. And that's actually called the constant of integration. And now let's have a look at the second example, which is the integral of x plus 5x cubed dx. And when you've got a sum of different terms that you need to integrate, then you just take each term in turn. So it's exactly the same principle. You just deal with each term one at a time. So don't get overwhelmed if you see lots of terms that you need to integrate in one integral. So here we've got x, so add 1 to the power and divide by the power so formed. So it's x squared over 2. And then we've got plus 5x cubed. So the 5 we just leave there as it is. And x cubed, we add 1 to the power to get x to the 4, and then divided by 4. So it's plus 5x to the 4 divided by 4. And don't forget that constant of integration. You always have to put plus c for when you've got an indefinite integral. And if you forget the plus c, then you're likely to lose a mark. So just make sure you remember that. And I'm going to leave it there for now for an introduction to basic integration, but there's so much more you can do. You can integrate some really complicated looking formulae, but it's always easy if you know how. So there's techniques like integration by parts, integration by substitutions, and I love making some more videos about that as well. So if there's a certain technique for integration that you'd like me to cover next, then just write it in the comments and I'll be sure to do that. And that's it for this video. As always, I hope you find it useful. If you do, please like and spread the word. Also, subscribe and hit the bell to turn on notifications so you don't miss out on any of my videos. I'm making a different one each week. So if there's a topic you'd really like me to cover, let me know in the comments below and I'll be sure to cover it. But that's it for now. Thank you for watching and see you next time. Bye bye.